Hello everyone, my name is Shima Bab Hadiashar. I recently finished my PhD at Institute for Quantum Computing, University of Waterloo. This is my talk for the 16th conference on the theory of quantum computation, communication, and cryptography. Here, I'm going to talk about one-shot quantum state redistribution and quantum Markov chains. This talk is based on a joint work with Anurag Anshu, Rahul Jain, Ashwin, Nayak, and Touchette. Quantum state redistribution holds an important place in the theory of quantum communication. In this task, there is a pure state rho R A B C, such that registers A and C are with Alice, register B is with Bob, and register R is with referee. Alice and Bob have access to a noiseless quantum channel and some shared entangled states. And Alice wants to transfer C to Bob coherently, such that at the end, the global state over registers R, A, B, C is close to rho in fidelity. This task is well understood in the asymptotic and IID setting and has communication rate given by a quantum conditional mutual information of R and C given B. Also, in the one-shot setting, there have been many efforts to characterize the cost of this task. However, all known upper bounds are suboptimal. In particular, in the case that register R is trivial, cost of all previously known protocols can be in the order of log of dimension, while the optimal cost is obviously zero because the desired state can be shared initially as entanglement between Alice and Bob. Let me also explain some motivations for starting this task. An information theoretic motivation comes from the fact that the asymptotic cost of state redistribution is quantum conditional mutual information. And so a characterization of the one-shot cost of this task gives us an operational one-shot analog for quantum conditional mutual information. There are several one-shot analogs known for other entropy quantities like von Neumann entropy, quantum relative entropy, and quantum mutual information. But a one-shot analog for quantum conditional mutual information with desirable properties is still unknown. The second motivation comes from the communication complexity area and direct sum conjecture. In the communication complexity setting, there is a function f with two inputs from sets x and y, and there are two parties, Alice and Bob, each given an input of the function f, and they want to compute the value of function f on their inputs with minimum communication using a noiseless quantum channel and some shared entangled states. Direct sum conjecture claims that the communication cost of computing n copies of f simultaneously is approximately n times larger than the communication cost of computing one copy. Of course, one way to compute n copies of f is to compute them sequentially and one by one. But this conjecture claims that computing them in parallel and at the same time would not help much in reducing the cost. For the case that the communication is one way from Alice to Bob, direct sum conjecture has been shown to be true by Jain, Radhakrishnan, and Sen in 2008. For the interactive setting, it has been shown that direct sum can be false if the number of rounds of communication is very large. This is a result by Anshu, Touchette, Yao, and Yu in 2016. However, if the number of rounds is bounded, let's say some constant, then it's highly believed that direct sum should hold and one way to prove it is through quantum state redistribution. In particular, a one-shot quantum state redistribution protocol with cost in the order of conditional mutual information can be used to derive a direct sum theorem for bounded round quantum communication complexity. Such a protocol is still unknown, and this was one of our main motivations for starting this task. So, motivated by these, we designed a new one-shot protocol with a smaller cost than the previous ones. The cost of our protocol is bounded by the difference between max relative entropy of rho RBC and sigma RBC, and the hypothesis testing relative entropy of rho BC and sigma BC, where sigma RBC here is a quantum Markov extension, meaning that its conditional mutual information is 0, so it's a quantum Markov state, and also its marginal on registers R and B is equal to rho RB, so it's an extension of the state rho. As far as we know, this is the first result that connects one-shot quantum state redistribution and quantum Markov chains. Our bound is tighter than all previously known quantum upper bounds. In fact, if rho RBC is a Markov state, then the cost of our protocol is nearly 0 and optimal. Also, the best previously known upper bound was a similar bound due to Anshu, Jain, and Varsi, where the minimization is only over the set of product states rather than the set of all quantum Markov extensions. In the case that rho RBC is classical, we can choose its Markov extension sigma RBC so that its marginal on registers BC is equal to rho BC. And so our bound reduces to a one-shot version of a classical conditional mutual information. Also, in general, the quantum conditional mutual information can be written as the difference between relative entropy of rho RBC and sigma RBC and relative entropy of rho BC and sigma BC. And as you can see, our bound is a one-shot version of this expression. And so our result gives an operational interpretation for a possible one-shot analog of conditional mutual information. To explain the high-level idea behind our protocol, let me first briefly explain a folklore zero-cost protocol for quantum Markov chains. As a result of the work by Hayden, Joseph, Pess, and Winter in 2004, it is known that if rho RBC is a Markov chain, then its purification, rho RABC, can be transformed through local isometries V sub A and V sub B to a state of this form, where registers AR, J prime, AC, and C are with Alice, and registers BR, J, and BC are with Bob, and condition on registers J and J prime, registers R, AR, and BR are decoupled from registers AC, C, and BC. So in order to redistribute C, controlled on J and J prime, Alice and Bob first embezzle out registers C, AC, and BC, and then they embezzle in the same systems such that now registers C and BC are with Bob and register AC is with Alice. So of course, this protocol only works for quantum Markov states, and we need to utilize more advanced techniques to make it work for any quantum state. For the rest of this talk, let sigma RBC be a fixed quantum Markov extension of rho, meaning that the marginal of sigma on RB is equal to the rho RB, and the conditional mutual information of sigma is 0. So our protocol consists of two ingredients. The main ingredient is a unitary procedure mapping registers BC to registers BC and some extra register T with two properties. First, it transforms sigma RBC to a product state between registers RB and CT, such that the marginal on RB does not change. And we denote the marginal on register CT here by tau. Second, when applied to the state rho RBC, it maps rho to a state kappa, which is not necessarily product, but similar to sigma, its marginal on systems RB remains unchanged. Now, since kappa RB equals rho RB, the Ullmann theorem implies that there exists also an isometry W from registers AC to registers ACT, which maps the pure state rho to the purification of kappa. Therefore, one can map rho to kappa by either applying this unitary U on registers BC or applying this unitary W on registers AC. The other ingredient is the state redistribution protocol due to Anshu, Jain, and Morsi, which we call the AJW protocol. As mentioned before, the cost of this protocol is bounded by the Vmax minus DH quantity when minimizing over product states. And it utilizes convex split and position-based decoding techniques to achieve this bound. Of course, this is a very cool protocol, but here to obtain our tighter bound, we use the AJW protocol as a subroutine and in a black box manner. So I'm not going into the details of this protocol in this presentation. Now let me explain the outline of our protocol. The high-level idea behind our protocol is to transform rho to the state kappa reversibly and then redistribute registers C and T in kappa using the AJW protocol, and at the end transform back the global state to rho. In particular, our protocol contains three main steps. This diagram here visualizes the distribution of systems at the beginning. Recall that initially, registers A and C are with Alice, and register B is with Bob, and their global state is the state rho purified in the system R. So in the first step, since registers A and C are with Alice, Alice can apply the isometry W to registers A and C. And this operation transformed the global state to the state kappa RABCT, such that now Alice holds registers A, C, and T. Now, in the second step, Alice and Bob run the AJW protocol to redistribute registers C and T in the state kappa. So after this step, the joint state of Alice and Bob is close to kappa, such that now registers C and T are with Bob. And so now that Bob has access to all registers B, C, and T, he can apply the inverse of U to map their joint state to a state close to rho. So at the end, the joint state of Alice and Bob and referee will be close to rho RABC. And now register C is with Bob as we wanted. In this protocol, the communication between Alice and Bob takes place in step 2 when they run the AJW protocol to redistribute kappa. So the communication cost of this protocol is the Vmax minus DH quantity of kappa RBCT and the product state kappa RB tensor tau CT. Recall that kappa and the product state are transformations of rho and sigma under the same isometry U. So the unitary invariance of entropy quantities imply that this class is equal to d max minus dh distance of rho from sigma, as we claimed. Okay, great. So now that we understood how the protocol works, it remains to see how to construct the decoupling unitary U. So this is the most technical part of our results. So I start with a simplified version of it for the GHZ state. So consider the case that register A is trivial and the state rho RBC is the GHZ state. A Markov extension of rho is this state sigma, in which registers R, B, and C are classical and maximally correlated. Recall that we are looking for an isometry that decouples C from RB in sigma. So in this example, this can be done simply by erasing system C condition on register B. So in particular, the unitary U looks like this. It maps the state ket J to this ket 0 state when register B is in the ket J state. This unitary maps sigma to a product state between R, B, and C, as we hoped for. But when applied to rho, the marginal of the transformed state on registers RB is the maximally entangled state, which is not equal to the marginal of rho on RB. So to overcome this problem, we do the following. First, we coherently measure register B by adding an additional register T in the maximally mixed state and making a copy of register B in T using generalized Pauli operator. In particular, we apply the unitary operation U sub 1, which applies the Pauli operator P sub J on register T if register B is in the state ket J. This operation transforms state rho to this state XC here, but does not change sigma because register B is already classical in sigma. Now, if we erase register C condition on register B using this unitary U2, which is basically our initial proposal for U, then U2 transformed sigma to this product state here, as we wanted, and it transforms the state XC to this state here, which we call kappa. So note that since Pauli operators are cos under multiplication and also all of them except identity are traceless, then tracing out register T in kappa will make J and K equal. And so kappa RB will be the maximally correlated state and equal to rho RB as we wanted. So to achieve the decoupling, it suffices to choose the unitary U to be the composition of U1 and U2, as it satisfies both desired properties. Okay, so this is how decoupling can be done for the GHZ state. Now, notice that a main property that we needed here is the fact that register B is classical in the quantum Markov extension of the GHZ state. Now consider an arbitrary state rho with quantum Markov extension sigma. In general, register B may not be classical in sigma. However, as I mentioned before, for the Folklore Protocol, Since a sigma RBC is a Markov state, there exists an isometry V which transforms sigma to this classical quantum state here over registers R, B, R, J, B, C, and C, such that register J is classical, and conditioned on J, registers R, B, R are decoupled from registers B, C, and C. Now, let rho R, A, B, R, J, B, C, C be the transformation of rho under this isometry V, okay? So then it suffices to redistribute register C in this new state. And now, since register J is classical in its Markov extension, as you can see here, we can use similar ideas as in the GC example to decouple register C from the rest of registers in sigma. In particular, the decoupling will be done by two steps of coherent measurement and conditional erasure. The coherent measurement step is similar to the GC example. For the conditional erasure, though, we need to use a coherent flattening via embezzlement technique due to Anshu and Jain, and a couple of more tricks to make it work. If you're interested, you can find more details about this step in our manuscript posted on arXiv here. So let me summarize. In this work, we introduced a new one-shot protocol with smaller costs than previous known protocols. Our protocol is optimal for quantum Markov states, and our result gives an operational interpretation for a one-shot analog of quantum conditional mutual information. Here we focus on upper bounds, and natural follow-up question is whether our bound is optimal, and to answer it, we need tight lower bounds. As far as we know, none of currently known lower bounds are tight, and so finding a tight lower bound would be an interesting future direction. Also, it is still open whether the cost of one-shot state redistribution can be bounded by the quantum conditional mutual information. As I explained earlier, such a bound will result in a new direct sum theorem for bounded bound quantum communication complexity. So with this, I would like to conclude my presentation. Thank you for your attention, and feel free to contact me if you have any question or suggestion.